In 1659, Pierre de Fermat challenged English and French mathematicians to find a cube whose sum of divisors equals a square. He gave the non-trivial solution 7 cubed plus 7 squared plus 7 plus 1 equals 20 squared, which turns out to be the only one when x is prime, a fact that can be proved by his method of infinite descent. In a letter to Franck Le Debussy, Fermat even claimed what has been proved for primes can be extended to composite numbers. Probably to his surprise, John Wallis replied with 8 composite solutions, being the smallest integers of 9 or more digits and 4 to 6 prime factors. Wallis further observed that each solution could be scaled by 7 to yield another solution. This follows easily with modern notation. If the sum of divisors of x sub I cubed is a square, say y sub I squared, then as long as 7 is coprime to x sub I, multiplicatively tells us that the sum of the divisors of the cube of 7 times x sub I is sigma of 7 cubed times sigma of x sub I cubed. But sigma of 7 cubed is 20 squared, so the result is the square of 20 times y sub I. André Weil analyzed the problem in his book Number Theory, an approach through history from Hammurapi to Legendre, ending with an incisive assessment. The reputation for Fermat's infallibility that some of his admirers have sought to build up for him is no more than a legend. Harold Edwards offered a more generous view in his book Fermat's Last Theorem, a genetic introduction to algebraic number theory. This is an excellent but very difficult problem, and modestly left his descent argument for prime x in the answers to exercises section, which we'll unpack step by step. Edwards considered the case when x is prime, reducing the problem to the Diophantine equation x cubed plus x squared plus x plus 1 equals y squared, which factors neatly as x plus 1 times x squared plus 1. We begin by analyzing the coprimality of the two factors. Any common divisor must divide the square of the first factor minus the second factor, which equals to x. Since x is coprime to both factors, any common divisor must divide 2, but they are not coprime. Otherwise, both factors should be squares, but x squared plus 1 cannot be a square. Therefore, the greatest common divisor is 2, and for x bigger than 0, we may write x plus 1 equals 2u squared, and x squared plus 1 equals 2v squared. Substituting x into the second equation gives the square of 2u squared minus 1 plus 1 equals 2v squared. Expanding and dividing by 2 yields this expression, which can be rewritten as u raised to the fourth plus the square of u squared minus 1 equals v squared. Thus, we obtain a primitive Pythagorean triple, since the sides are consecutive, except when u equals 1, hence x equals 1, and the trivial solution u cubed plus u squared plus 1 equals 2 squared. For x bigger than 1, we proceed by considering the parity of u. If u is odd, we parameterize the primitive Pythagorean triple as u squared equals p squared minus q squared, u squared minus 1 equals 2pq, and v equal p squared plus q squared, with p bigger than q, both bigger than 0, coprime, and of opposite parity. Edwards then states without further comment, u equals the square of p minus q minus 2 times q squared, and that p minus q is a square. Thus, the square of q squared plus 1 equals q raised to the fourth plus t raised to the fourth, which clearly requires some unpacking. Substituting u squared into the first equation gives 2pq plus 1 equals p squared minus q squared. Hence, 1 equals the square of p minus q minus 2q squared. So, 2q squared plus 1 equals the square of p minus q. To prove p minus q is a square, we turn to the primitive Pythagorean triple u squared plus q squared equals p squared. Since u cannot be even, as p and q are of opposite parity, we parameterize u as r squared minus s squared, q as 2rs, and p as r squared plus s squared. with r bigger than s, both bigger than 0, coprime, and of opposite parity. Then p minus q equals t squared, as Edwards asserted. Finally, from 2q squared plus 1, we reach t raised to the fourth. Edwards cleverly noted that the square of q squared plus 1 minus q raised to the fourth equals 2 times q squared plus 1. Hence, the square of q squared plus 1 equals q raised to the fourth plus t raised to the fourth, which is impossible. Euler proved this by infinite descent. There is no trivial solution to retrieve here, since q and t squared are both bigger than 0. If u is even, we parameterize the primitive Pythagorean triple as u squared equals 2pq, u squared minus 1 equals p squared minus q squared, and v equals p squared plus q squared, with p bigger than q, both bigger than 0, coprime, and of opposite parity. Substituting the first equation into the second gives this expression. Hence, q times 2p plus q equals p squared plus 1. Here, Edwards states that p is even and twice a square, which can be checked easily. If p is odd, then q must be even, writing p as 2n plus 1 and q as 2m, and substituting in the previous equation gives 4 times an integer equals 2 times an odd integer, a contradiction. Hence, p is even and q is odd. From u squared equals 2pq. 2q cannot be a square. Hence, p equals 2 times t squared, just like Edwards stated, and q equals s squared. In 2pq plus q squared equals p squared plus 1, we add p squared to both sides, yielding the square of p plus q equals 2p squared plus 1. Therefore, the square of p plus q minus 1 can be factored as p plus q minus 1 times p plus q plus 1, which equals 2p squared. Hence, it is equal to a times t raised to the fourth. Since p plus q plus minus 1 are even, set a equal p plus q minus 1 over 2. Then a times a plus 1 equals 2 times t raised to the fourth. Given that a and a plus 1 are coprime, one is a biquadrate and the other twice a biquadrate. So we have two cases. In the first case, a plus 1 equals b raised to the fourth, and a equals 2 times c raised to the fourth. Hence, 2c raised to the fourth plus 1 equals b raised to the fourth. Note that b and c coprimality is inherited from the coprimality of a and a plus 1. Edwards applies the trick again, observing that the square of c raised to the fourth plus 1 equals c raised to the eighth plus 2c raised to the fourth plus 1, which equals the sum of two biquadrates, which is impossible. Note that from a equals p plus q minus 1 over 2, since p is equal or bigger than q plus 1, then a is bigger than q, which is bigger than 0. Hence, b and c are bigger than 0, so we cannot evade a square being the sum of two biquadrates. In the second case, a equals b raised to the fourth, and a plus 1 equals 2 times c raised to the fourth. Hence, b raised to the fourth equals 2c raised to the fourth minus 1. Then the square of c raised to the fourth minus 1 equals c raised to the eighth minus 2c raised to the fourth minus 1, which equals a difference of two biquadrates, which is impossible for b and c bigger than 0. Fermat proved this by infinite descent. Now let's check the few remaining cases. If c equals 0, then the square of c raised to the fourth minus 1 equals minus b raised to the fourth, which is impossible. If b equals 0, then a equals 0, so p plus q equals 1, contradicting p is bigger than q, which is bigger than 0. Finally, we check c raised to the eighth equals b raised to the fourth. Since b and c are coprime, we must have b equals 1 and c equals plus minus 1. So a equals 1. From a equals p plus q minus 1 over 2, we get p plus q equals 3. Hence, p equals 2, q equals 1, so u equals 2, and x equals 7, yielding the solution 7 cubed plus 7 squared plus 7 plus 1 equals 20 squared. There are also trivial solutions arising from small values in the system, x plus 1 equals 2u squared, and x squared plus 1 equals 2v squared. From u equals 0, we obtain x equals minus 1, yielding y equals 0. From u equals 1, we obtain x equals 1, giving y equals 2. From u equals 0, we obtain x equals plus minus 1, reproducing these solutions. The case v equals 0 gives x squared equals minus 1, which is impossible. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.